Every single minute, users upload over 500 hours of video to YouTube. That translates to terabytes of raw, unstructured data slamming into the network continuously, 24 hours a day. This creates an extreme engineering paradox. The system must accept monolithic video files, sometimes up to 256 gigabytes in size, and make them globally streamable across thousands of different device types and network conditions, usually within minutes of the upload finishing. Standard web architectures collapse completely under this specific throughput. Traditional load balancers and application servers are built for millions of lightweight text and database queries, not gigabyte-scale continuous binary streams. If a traditional application server attempts to process a massive media file synchronously, it locks up connection threats for hours, memory exhausts, CPUs throttle, and the entire server tier crashes under the weight of concurrent upload requests. To survive this intake, YouTube relies on a fully decoupled, highly asynchronous architecture paired with custom hardware accelerators specifically designed to process video at a warehouse scale. To understand how this infrastructure actually operates, we have to follow the exact chronological path of a single video upload, starting from the user's client application, moving through the deep data center storage, and ending at the distributed edge cache. Servicing billions of daily viewers requires abandoning standard software abstraction. The solution demands deep, intentional co-design of both the hardware and the software. The upload process begins before a single byte of video is transferred. The user's client application first contacts the API gateway to initiate a request. This initiates a metadata handshake. The upload service validates the user's credentials and reserves a unique video ID in the Vitesse relational database. The application server handles this logic without ever touching the actual video data. Routing heavy, gigabyte-scale video bytes directly through the application server layer is a catastrophic network risk. It would instantly saturate the application bandwidth, choking out regular API requests. To bypass the application servers entirely, the API generates a pre-signed URL. This cryptographic token grants the client application temporary, highly restricted permission to open a direct, high-throughput pathway straight to the storage cluster. The client application then slices the raw video file into chunks, typically between 10 and 50 megabytes each. This client-side chunking guarantees that if the user's network connection drops, the system only has to retry the failed chunk, rather than restarting the entire upload. These segmented blocks are routed directly into Colossus, Google's next-generation distributed file system. Within Colossus, specialized workers called D-servers act as the network-attached disks. These nodes physically receive and store the raw binary data directly from the client. Meanwhile, Colossus curators manage the namespace. Backed by the high-performance big table database, these curators map the physical disk locations of every single video chunk, orchestrating the file system without ever holding the raw data themselves. By strictly separating the control plane that manages the metadata from the data plane that routes the raw video, the ingestion pipeline achieves the fault tolerance necessary to absorb exabytes of daily traffic. Once Colossus confirms the raw file is safely stored, it emits an asynchronous event message. This wakes up the transcoding farm. The transcoding farm executes the most mathematically demanding phase of the pipeline. It must convert the single raw uploaded file into dozens of optimized variants across multiple resolutions, bit rates, and codecs. To schedule these complex dependencies, YouTube utilizes a directed acyclic graph, or DAG. The DAG orchestrator allows the system to execute thousands of independent processing tasks in parallel. Peripheral branches of the DAG trigger immediately. While the video is queued, separate worker nodes extract the audio stream, generate thumbnail frames, and run automated content ID algorithms to detect copyrighted material. The central branch handles the multi-format video encoding pipeline. Every video must be encoded into legacy formats like H.264 for older devices, alongside highly compressed modern codecs like VP9 and AV1. The transition to these highly efficient next-generation codecs created a severe compute crisis inside Google's data centers. While AV1 delivers superior video quality at lower bandwidths, it requires roughly 200 times more compute time to encode than legacy H.264 formats. Running this math on standard CPUs fractures the basic economics of data center power and cooling. Algorithmic complexity has vastly outpaced the evolution of general-purpose CPUs. Standard horizontal scaling, simply adding more server racks, became economically impossible. The compute bottleneck forced a pivot to silicon design. This piece of silicon is Google's Argos Video Coding Unit. It is an application-specific integrated circuit, or ASIC, engineered from the ground up exclusively for warehouse-scale video processing. Traditional server encoding processes are highly inefficient. To generate a 1080p, a 720p, and a 480p version of the same video, a CPU must decode the exact same raw source file from scratch multiple times, wasting massive amounts of compute cycles. The Argos chip solves this through multi-output transcoding. The ASIC decodes the raw video exactly once, scales it internally, and feeds the frames directly into multiple parallel hardware encoders. Because the encoders operate simultaneously on the same chip, they share critical control parameters. When the hardware detects a scene change or a camera flash, it shares that math across all target resolutions instantly, preventing redundant calculations. By hardwiring the codec math directly into the silicon, the Argos VCU achieves a 20 to 33 times efficiency improvement over highly optimized software running on traditional CPUs. This bespoke hardware results in a 90% reduction in power consumption per transcoded video. Investing millions into custom silicon development is the only viable engineering method to slash data center power usage, meeting the demands of planetary-scale media. With the transcoding complete, the video data must leave the central processing farm and move out toward the global distribution networks. The multiple resolutions generated by the Argos ECU are not stored or delivered as monolithic, continuous files. During the packaging phase, the continuous video streams are mathematically sliced into independent segments, typically containing between 2 and 10 seconds of playback. The system generates a manifest file, a crucial index document that maps the precise URL location of every available video segment and correlates it to its specific quality level and codec. These independent segments are then proactively pushed out to the content delivery network, caching the files on edge servers geographically located as close to the end viewers as possible. When a user hits play, the client-side video player relies on adaptive bitrate streaming to request these chunks sequentially. The player constantly measures the user's local network speed. If the Wi-Fi connection drops, the player reads the manifest file and seamlessly requests the next 5-second chunk from a lower resolution cache. When the connection recovers, it requests the high-definition chunks again, preventing the video from buffering. The continuous, flawless playback you experience is an illusion. It is the result of a frantic, real-time negotiation between a bandwidth-aware client application and a globally distributed edge cache. Looking at this complete end-to-end schematic, the true scale of YouTube's system architecture becomes clear. Ingestion bypasses the application servers entirely, using pre-signed URLs to stream heavy data chunks directly into network-attached storage disks. Processing relies on DAG orchestration to feed those raw chunks into custom ASICs, bypassing CPU limitations to decode and scale multi-format video in real time. Delivery fragments the resulting files into granular segments, distributing them to the network edge for adaptive retrieval by intelligent client players. At every step of this pipeline, the control plane is absolutely decoupled from the data plane. Metadata and logic are handled by specialized databases, while the heavy binary payloads are routed through optimized storage and network pathways. Standard software bottlenecks are eliminated through bespoke network protocols and highly specialized physical hardware. Achieving true planetary scale requires engineers to stop relying on off-the-shelf software abstraction. The system must be rigorously redesigned from the bare silicon all the way to the network edge.